All right, welcome everybody. We'll get going with this one. So today we're talking about data reliability, and really how it's the dark horse in the HPC world. It's something that we often don't talk about. It amazes me how many RFPs that come out that don't talk about reliability. So I wanted to dive in a little bit and talk about some of the scenarios and some of the situations and do some comparisons against kind of what the rest of the IT world looks at, and then how we address this moving forward. So I was actually, as I was thinking about this session, I slept lightly last night. So it's just one of those. I was tired. I get up and I go, it's just kind of funny. It's actually like an analogy on how the life of someone dealing with HPC data has to be dealing with it. It's like, how do you sleep at night when you know that the reliability and the chances of those systems to remain up and running on a regular basis is quite low? So I looked at it and I thought, you know what, I'm just going to throw a slide together and just kind of put a comparison in. We think about the enterprise or the cloud experience. World's a little bit different. I know this is kind of a joke because I don't know anybody that runs an IT department that doesn't have their hair on fire half the time. But the point is, the environments are reliable. Systems are made to be set up and run. And when people are buying equipment, they know that the equipment that they have is secure. When you're looking at cloud experiences, the availability of the cloud environments are high, durability is really high. So it's just kind of looking at those things. But yet when you jump onto the HPC experience, it's like, are we all just sitting on a little island? We're not part of the real world over here. When things get on fire, it's like a cry for help. Somebody, what are we going to do? So what do we often do? We become experts on how to resolve all our own problems. So let's look into some of these things and see what kind of situations we typically see, at least from the data side of the world. So if I look at some of the situations, the first bullet, I could have told you this one 10 years ago. I could tell you this now. I could tell you this in 10 years. But data is always, it's ever growing, right? It continues to accelerate at a faster pace. Capacity is growing faster than drive capacity. So we have to deal with building bigger and bigger systems in order to support the data infrastructure our applications require. Whether it's a group within your team, whether it's research environments, whatever it is, there's just a growing number of components. And the more you grow, the more reliability becomes a challenge. Whether it's more commodity type drives, NICs, systems, you name it, this becomes a challenge. But as we go through this whole thing, the enterprise works on resolving some of these challenges by putting reliability metrics in every single storage RFP that's out there. Any type of a data platform. I came from the enterprise world in the past. I came from the cloud world in the past as well. And you would be remiss to see anybody deliver an RFP that didn't ask, how reliable was the storage system. But yet, as we look at that, we look at the need for productivity. One of the big things is getting cluster downtime to a minimum. When we're talking about unstable scratch storage, really the crux of HPC, 34% of customers researched or responded saying that they had at least one downtime per month. I don't know, where you guys stand on that. It'd be interesting to see that, but it's pretty common. And as I talk to different people, I talk to customers, whether it shows or you name it, it's amazing how many people have said, "Oh yeah, we just dealt with a down system last week." And then also 41% of those surveyed said downtime events last more than a day. 17% said more than a week. So we always just kind of assume complexity and structural, all kinds of different things in place to make sure that our systems stay up and running. And especially in the island of HPC, we're dealing with storage environments that are often not a typical IT data person is not going to know how to manage a parallel infrastructure, right? They're not going to know how to do some of these clustered environments. So it becomes specialty knowledge for all of us. And again, enterprises often require more than 3 nines of uptime in this. So another thing too is, the shared nothing reliability model has become the mainstay in the cloud. So when I say shared nothing, I'm talking about software-based erasure coding across storage environments versus the traditional hardware RAID, where you've got a bunch of hard drives in an area and you have a hardware RAID controller sitting on top of it. It handles drive failure pretty well, but it doesn't handle broader failures as you move forward. But also in the cloud, when you're talking shared nothing, it doesn't matter what the media types are underneath it as well. So you can have hard drives, you can have flash drives. It doesn't matter what those are. There is a reliability piece built across all of those. And so I think I said shared nothing twice here, but don't mind me. So and then the question I ask is, like, why is HPC exempt, right? Why do we not put these, why do we not care about some of this stuff? Well, I guess maybe we all care about it, but I look at it as precedent should never define the requirement. When we look at delivering, building systems, we want to make sure that our systems are up and running. We want to make sure that our researchers or our engineers are productive and those systems don't fail. And if there is sort of a failure, what are the paths out of that? And really, performance and reliability are both important. When we talk about scratch space, I think the common thread is, let's make it as fast as it can be, but then not worry if it's going to crash. The problem is anytime a system crashes, we do have to deal with the repercussions of that. And the answer is there are solutions that are out there. So let me just talk a little briefly about Panasas before I move on to some more of the detail here. So Panasas, we're a high performance data storage solution. We were founded in '99, 23 years ago, 24, I guess, by the co-inventor of RAID. And you're going to see me talk about RAID pretty consistently throughout this, but and I'll have some clarification points there. But Garth Gibson founded us back in '99. And we really were a pioneer in the scale-out NAS and parallel file system world. When it comes to that, it's, we have PanFS as our file system that runs. Most of you all know of Luster. It really came out of the exact same labs that Garth was working in back in that time frame as well. But we are the only parallel file system out there that has reliability designed in, and I'll talk a little bit more about that. And we focused on just making life better for our customers in the ways of the complexity of some of this becomes quite heavy. So let's provide a simple interface to it. Let's provide an easy way to manage it. Let's make sure it's reliable so you can do your best to set it and forget it, but yet you can scale as your data environments scale. So as we've grown over the years, for a long period of time, it was about, we delivered a complete solution of hardware and software, our own dedicated platforms, and we were hardening our PanFS architecture. At a point about 6 years ago, we determined that, there's no point in building our own hardware platforms, and we went to a more software-defined model and delivered the PanFS software on more commercial off-the-shelf hardware. And the last year, we expanded that into new areas, flash, more dense platforms, as well as, I don't have on here, we released earlier this year an edge platform for those small form factor environments. But as we move forward, really the growth is around expanding our software capabilities. Now that there's a lot of different places that you can put your data, being able to have mobility and visibility across that. Broaden our hardware supportability matrix, so delivering new architectures, delivering new systems, different areas that we could build, because we are software defined now at this point. It's a matter of delivering solutions that allow us to grow into more of a SaaS based type of an architecture. whether that's, Kubernetes, cloud, the container environments. There's a lot of different scenarios that we can go into, but that's where our focus is as we move forward, making that software much more portable. So just a simple kind of maybe a marketing slide here, but just a key areas for us. Performance, obviously, we are in this HPC world, making sure that we can get the most out of the underlying system and delivering the reliability piece. Again, this is built-in reliability in the file system. I'll dive into that a little bit. Making sure it's flexible so that you can get this in different areas and easy to use. And this is a big one. One of the biggest things here is, if I look at some of the other storage solutions in this space, typically require a team and typically are quite difficult to operate. It's you get very specialty knowledge in order to operate some of these things. And our goal here has really been to make our platforms as easy to use, because I know in the HPC world, the more events that I go to, the more I see gray hair like I have on my chin here. But it's just one of those that, getting new talent in to manage these environments is becoming tougher and tougher. So let me dive into this just a touch. So a parallel architecture, just to describe here, this is specifically our Panasas architecture, how we operate, what does our system look like? You'll see up at the top the clients. So the clients are out there. That's all of your server clients, whether it's 10, 100, or 1,000, they're sitting out there. We have the direct flow drivers on there. Or on the left side, you can see where you can either go through NFS or SMB even to access the data environments. But direct flow is kind of the bread and butter. That's what gives us the that direct path to storage. And on the left, in the middle there, you see our active source directors. Our directors are kind of the managers, right? They manage the metadata, they manage the information, they manage where data is located within the storage cluster, and then how and who the clients each talk to. So when it comes down to the storage nodes at the bottom down here, that's where we crank out the performance of the platform. So each client accesses storage on one of the storage nodes down below, but then we actually distribute the storage across nodes to manage congestion, to manage different scenarios where storage access could become a problem. What you'll notice with this type of an architecture is this is quite different from a traditional enterprise type architecture. So this is where we really diverge from my earlier comments about enterprise requirements. But enterprise often is, a dual node HA type of a platform where you have all your clients going through one head node, and if one head node fails, you fail to the other head node. In this case, every client has access to its storage directly, and our directors on the left here manage who has access to what. And I'll talk about the reliability piece as we move forward, but what you'll see here is, we distribute the storage across all of these different storage nodes such that if anything fails or anything goes down, we have the ability to recover it, and it's all built into the file system. And I'll just, talk a little bit about what does that mean? So if we look at POSIX file environments, we layer the files over the top of our OSDs, which are our object storage devices. So everything within our system internally is an object, not like the objects that with S3, but more of a data object inside. But that's nothing that you worry about on the top end. You access everything through a file architecture. But each file is individually erasure coded. And when we say that each file, I'll dive into a little bit more here, but not just the storage environment that is protected with erasure coding. We do this on an individual file by file basis. And when we look at a typical node +2 type of a erasure coding, this has a 16% overhead compared to some of the other models that are out there where we look at redundancy. 3 copies of everything in a cloud environment can be very heavyweight, right? So when you're looking at how many copies you have of something out there for redundancy, that becomes quite significant. And if you're moving that into a data center, or if you're doing that via S3 object in a data center, that's something that you actually have to account for, that triple the actual physical requirement in order to support the protections that you require. And then reliability is driven by recovery time after failure. So we all know that hard drives are going to fail. That's been a common theme for decades. A hard drive is often one of the least reliable component within the system. So it's a matter of how do you address failure when hard drives do fail. It's not a matter if they fail, it's a matter when they fail. So in this case, when a drive fails, what do you do? So when you go back and you recover that failure, you'll recover that drive and remain giving access out to the actual file system or to the applications. But in a common practice model, which I'll talk a little bit more about further ahead, but a common practice is to have like a RAID 6 type of an architecture, which is 4 storage drives with 2 parity drives. And what that means is you lose 1 drive, you can recover with the first parity, but you can actually still continue to operate. But a second failure means the systems are down. So what happens is the longer it takes for you to recover from 1 drive failure, the more likely it's going to have a second failure happen. So what you want to do is make sure that you have scenarios that can support fast recovery times, and to do that on this dual parity type of an architecture. And this is the same trade-off that one would see with a hardware-based RAID structure, but it's also how we handle in a software erasure coded model that we do. In our case, all of our storage nodes or object storage devices in our in the cluster that you build, the storage cluster that you build there, is associated as part of the recovery. So the bigger that your system is, you get better recovery times, right? So you're able to distribute that across a broader set of nodes. So the speed of recovery becomes much faster. And then lastly here is our directors. They manage the metadata and they are stateless. We actually have no data inside of the directors. So when it comes to any sort of failures on the director side, we can fail over our metadata control and metadata management inside of our systems. So something that allows for an additional layer of, if you assume everything's going to have a problem at some point, do you have a recovery mechanism for any one of those failure scenarios? So if I look at RAID as an option here, or as a comparison here, I think I'll be remiss to say that we are actually RAID. It's just an easy way to talk about it. I mean, we are erasure coding, which means that we actually distribute data across every node. And obviously RAID stands for redundant array of independent drives. So anyway, so it's this is just more for comparison's sake. But if you look at RAID 0, every single node has its own access, and there is no redundancy in that type of scenario. And then you go to the one in the middle here, you got RAID 5, where you've got 4 drives of data and 1 drive of parity. And that parity is, so you can help reconstruct if one of those drives fails. And then RAID 6 is 4 drives of data and 2 drives of parity. So if one of them fails, you can reconstruct, but you can continue to operate while that reconstruction happens. And then RAID 10 on the far right over here is kind of a different scenario. It's a RAID 5 structure, but duplicated. So it gives you a lot of protection, but it also with the limited performance drops if there is a failure. But in that case, it does take twice the data. So your RAID efficiency number drops more significantly when it comes to a RAID 10 architecture. If you're only doing 2 drives of parity for every 4 drives, a RAID 6 architecture is much better. And then we stripe that data across the stripe size 3, and then we can do stripe size 6. So we can actually stripe this across a broader range because of the inherent characteristics of how we do things with erasure coding. But just as a note is, we can do this per volume, we can do this per directory, or we can do this per file. And a lot of the times, a lot of our customers actually pick a standard and stick with it. But one of these things is we look at this on a per file basis. When we're talking about scratch space where you may not care as much, you don't actually have to have the storage platform or a large volume of the platform be dedicated to that unresilient scratch requirement. You can actually do that on a file by file basis. So thinking about how you would lay out a storage environment, you could say, hey, I have, maybe I have a 1 petabyte system and I have 100 terabytes of scratch space required. I could either just allocate 100 terabytes for scratch, or I could say everybody that is got a scratch, that is a scratch identifier, could actually just say those files are going to be scratch files, and they'll be done on a per file basis. So it really allows a lot of flexibility in that type of scenario, and how you actually lay it out can affect performance, right? So if you don't have to deal with any sort of a RAID overhead, then you actually get a better performance, but you limit reliability. If you can do that on a file by file basis, you can have your entire system reliable, except for a few small file environments that don't need to be. And so kind of, I want to just like to spell this from what does this all mean? Okay, great. So we have node-based erasure coding. This means a shared nothing architecture. When we look at what is the cloud, the massive cloud providers gone off and done, they've built their environments to scale without having, those single points of failure, so they can do a shared nothing environment that works well. Lose a drive, no big deal. Lose a network link, no big deal. Lose a node, no big deal. We can recover from all of these types of scenarios. Because the erasure coding is done at a higher level by software, we don't have to rely on an individual hardware platform that could fail, or any component within it that could fail. We have that flexibility to handle a lot of different failure modes. And then the second one here is all storage nodes. Again, I kind of mentioned this, but all storage nodes participate in recovery. So the bigger the system, the more reliable it becomes. This is not a common theme, right? This is not what you look at. When you look at a pairwise HA architecture, you are always going to have your protection model at that pairwise level. So you lose something, you can fail over to the other node, but if you lose something in that communication process, you could lose the entire node altogether, right? So there's different ways of looking at this. But as we scale, also, we distribute that reliability across more and more and more nodes. So the faster recovery time means better reliability. So a 1 petabyte system may be a certain level of maybe a couple of nines of reliability, but as you add nodes, that continues to increase the bigger you get. And then, as I kind of touched on here as well, per file erasure coding, is kind of a better everything, right? Less chance for data loss, if things get really bad. And what I mean by this is if you lose a node, your files are striped in different ways, right? Your files could be striped in across 10 other different nodes, and then different files could be striped in different locations. So if you actually had one of those really bad situations where a couple of nodes went down at the same time, your chance of data loss is very limited. But on top of that, if you did end up with data loss, you would know exactly what files were impacted. You wouldn't have to sit there and say, oh, what was lost in this entire volume environment? No, you know exactly which ones they were, because they all have different stripe characteristics across the overall cluster. And again, as I mentioned, with the scratch versus standard storage, you have that flexibility. If it's scratch, if it's standard, campaign, whatever the scenarios are, you have the flexibility in doing the erasure coding on a per file basis. Before I do a comparison. So how is your RAID different than others? So actually, okay, that was like a perfect timing. So when we look at, oops, let me back up before I go there. So when we look at how we compare against different other RAID architectures, One of the big things, and this is the most common in the industry right now, is hardware RAID. So every single hardware system has a hardware RAID controller that sits on top of it that manages drive failures underneath. And so if you lose a drive, that hardware environment, that node will work on recovering the data from that drive and repairing the data, do a full rebuild of that, and continue to operate. Obviously, it depends on what your what's the word I'm looking for? Anyway, your backup. So you have a few extras, spares. There's the word. So you have a few spares, typically in an environment. So it'll rebuild the drive on a spare, and then you can go out and toss that drive. But that is on a node by node basis. And as I'll show here in a moment, a node in an HA scenario, it would be on one of those HA nodes. If you lose anything that's in the control component of that or the head node side of it, if you're not able to recover and fail over to a secondary side there, then you deal with a different type of a situation. RAID in a typical config only supports hard drive based failures. In our case, we do software level and we do it at a higher level. So our RAID is at a node based level, not at a drive based level. So that's where when I say that if a link goes down, or if a hardware motherboard fails, or a drive failure, we handle all of those the same. Oops. All right, so let's compare. So I showed you our architecture before, which is, we have our OSDs, or our object storage devices, or our in storage pieces, and then the clients talk directly to them with a director that manages everything. So then in a Lustre scenario, it's actually the exact flip-flop image here, but think of it, if you're looking at our other one that I showed you from a top down, this one's from the bottom up. So you've got all the clients down here at the bottom, and they talk with their individual storage nodes. And off to the left, you see there's management, metadata and management servers. So on these ones, this is where all the metadata is managed. And inside of those metadata servers are hard drives that keep all of the metadata. So a lot of times you have, in that scenario, you have to do an HA type of a pair, or you do some sort of a situation to protect against failures of those metadata data servers, because they control the keys to the kingdom. If anything happens on a metadata server and you lose one of those, everything else is gone, everything. So when you look, as you go across to the right, you got a D&E metadata server, so you've got more, and you can continue to add metadata servers on there. And then off to the far right is the object storage targets. So kind of in a way similar to how we call them object storage devices, they have them object storage targets. But you'll notice these crisscrosses on each one of these. This is representative of the HA scenario. Every single node in a cluster, in a Lustre environment, requires HA if you want to have any sort of protection. There is no reliability built into the Lustre architecture. There's no reliability built into the Lustre file system itself. It is all handled outside. So that's where a storage node must have HA in order for you to be safe against any sort of a failure of one of those nodes, because there is no reliability characteristic on top of that. And again, I don't show in this one here, but there are gateways as well if you want to access NFS or SMB. So just as a kind of from a namespace standpoint, Panasas provides many volumes. Our top level, our entire system is called a realm. And then inside the realm, we have blade sets. And then inside those blade sets, we have volumes. So all of our mounts are global or per volume. And each volume gets its own metadata services and quota. And we can do up to 3,600 volumes per realm. And Lustre provides a shared POSIX namespace. So you get your D&E, allows multiple metadata targets, and an OST pool allow different hardware types in a single namespace. So kind of how we use blade set, they have an OST pool. And then Lustre quotas and project quotas can be used to manage the space. So some similarities there in just kind of how the file system operates. But now let's talk about data durability. I mean, this is really the key here about, what this webinar is about. So file level durability scheme. On a Panasas system, we do, and I told you before, it's erasure coding, but it's equivalent by design to a RAID 5, 6, or 10 architecture, and it can be set at a file base on a per file basis by the file system itself. In Lustre, there is no file level durability in the Lustre system at all. And so actual file level durability, that is a patent that we have. So that is something that Panasas does and does alone. And it gives an additional levels of flexibility, as I mentioned before. But again, durability is determined by the target's implementation, so the OST implementation. Now, a loss of a single disk. So in our case, in a Panasas case, the director will run a recovery process to restore to full durability. So when a drive fails, the director will be notified, and then the applications will either be pointed to a different location if they need to be, but they will manage the entire recovery process of that. In a Lustre scenario, the targets deal with it. It is not a part of the file system. Again, it's kind of how I mentioned before, that HA node for the OST on a Lustre system is the only thing that's managing the reliability of a drive loss. So normally this is hardware RAID within each target handling that drive loss. And the third one here is, what about a total loss of a node? So a Panasas OSD or a Lustre OST. In this case, the director runs a recovery process across the remaining storage nodes to restore the full durability. Again, because everything is distributed across the nodes, not across the drives, we can actually go ahead and recover on this. In the case of Lustre, a loss of all object data on a target is what happens, right? You lose everything there. That node is gone if you lose the node. Often a traditional pairwise HA environment is used against target failure. So there will be, if there is no HA pair on those OSTs, that data is gone, goodbye. And it is not part, again, because it's not part of the file system. And then what about a total loss of a director or a Lustre metadata target? There is no data on the director itself in a Panasas system. The services all log their data into the actual storage systems so that we can actually distribute that across and provide the same failure mechanisms if any sort of a node is lost. When a director is lost, that data is still accessible, and we just fail over to another director. And in a typical system, we have a minimum of 3 directors running, and then they grow based on some of the other performance requirements. But if you lose a director on a Lustre system, that's a complete loss of data, as I mentioned. There is no way to recover if you don't have the map to the data itself, so it's gone. So that was it. I want to just kind of highlight here, really from our standpoint, reliability is the key for any IT deployment environment. We seem to forget this, and in the HPC world, it's a bit of a different space. But I mean, I could ask any one of you. I mean, do you remember your last HPC outage? This is something that is quite common, as I showed you, and this was an analysis that we did with one of the analysts that we worked with, and they did a kind of a summary across and interviewed a bunch of different people and came up with the results of that one. That was Hyperion. And and data loss as well. So I don't have metrics on that one here, but it is another type of a common scenario where data can be lost in this. And as I said, I was up last night thinking about my presentation to all of you today. But I mean, when we talk about these IT scenarios, it's like, it would definitely keep me up at night. Everyone is affected by downtime. It usually is a productivity impact. And anyone that's managing the systems is, the hair goes on fire, and we got to figure out how to get that system back up and running. HPC is not on an island just because the open source solutions out there do not have reliability built in. And just want to highlight here, I've got a QR code on the right. So we will be at SC23 this year, and that's coming up in, I think, just like 3 short weeks. So I'd love you guys to come out and have a chat with us. You know, we've got oh, I didn't put the booth number in here. Anyway, but you can actually come by, see us, and also schedule a time to meet with some of our experts. So whether they're our technical team, we're actually going to have a whole host of architects there, just a lot of people there to help answer questions and talk to you in detail about how some of these scenarios that I touched upon can really fit in your type of an environment. So yeah, scan that one and you can go click on that link and sign up for a meeting with the team and see where you can go from there. And before I wrap up, let me jump to a couple of questions here that I see on the chat at the summary illustrator. Okay, there's the book of meeting link. All right. Let's see. Is luster for luster resilient? Let me see. For luster resiliency, it will get better with larger platforms as well, correct? And no, actually, so the interesting thing about as the system, a luster system grows, the reliability is limited to the node reliability architecture. So as you scale it, you actually decrease because the one of the things, I mean, it's not a massive decrease, but what you do is you get your hardware RAID controller on an individual node that can recover if a drive fails. And then you also have the HA. So if one of those nodes goes down, you could fail over to the other corresponding node. And that's the definition of your reliability characteristic. But as the system grows and gets larger and larger and larger, one of our biggest customers has 1,500 storage nodes. In a situation like that, the chances of having multi-nodal failure because of drives becomes higher and higher, right? So how do you address that in a luster scenario? Because that hardware RAID is defined on the node basis, you actually have the opportunity for more and more nodes to fail. So it actually will bring your reliability characteristics down. But in a case with Panasas, again, as you grow, because our rebuild is striped across the nodes that are out there, as the system gets bigger, that rebuild time gets shorter. So you actually get an increase in reliability. So it's like it's a different way things are done, but the way that we've built it is so that you can scale and scale and scale and not get a negative impact, but actually get a positive impact. Let's see, any other questions out there? Let's see the chat. Okay. Oh, hey, and I saw it in the chat. So we will be at booth 437 at SC23. So come and see us, even though I don't have that 437 in the bullet here. But either way, yeah, come see us or schedule a meeting and we'd be happy to talk with you. So with that, I will let you guys go and thank you for joining us today and look forward to talking to you in a few weeks. Goodbye.